All right, well, welcome to the last few sections. Again, chapter 13. We talked about arithmetic or the arithmetic for these lists of numbers we call sequences. And to get from one to another, we had that what was called constant difference, D. All right, now we're going to get to geometric. And since that constant difference was either adding or subtracting, which is why we called it arithmetic or arithmetic, what do you think geometric is going to be? What did you learn after adding and subtracting in elementary school?
Multiplying and dividing.
Very good. But if you had a choice, would you choose adding or subtracting?
Adding or subtracting?
Which one? Adding or subtracting?
Adding.
Yeah, definitely. Subtracting is a little bit more difficult. Not difficult, but more difficult. Well, if you had a choice, what would you rather choose? Multiplying or dividing?
Multiplying.
Mm-hmm.
Well, now we're going to restrict it to just that, okay? And we're going to call these geometric sequences, and how we get from one to the next is now going to be by only multiplication. Remember with the arithmetic, it was a little bit different. With arithmetic, we used arithmetic for that constant difference. And yes, you could either add or subtract. Okay, for this one, we are going to only multiply. And you guys will see why, hopefully, because if I gave you a list of numbers, right? If I told you, all right, well, let's start with a 2. And then I'm going to double it each time, right? So I could even have started with 1, and then 4, and then 8, and then 16, and so on. What if I wanted to go the other direction? All right, you guys know how I got from one to the next was multiplying by a 2, obviously. But what if I wanted to go the other direction? What if I wanted to rewrite it from right to left? And I said we had 32, and then 16, and then 8, 4, 2, 1, a half, so on. What would you tell me we're doing here to get from one to the next?
Oh, that's doubling.
Good. What would you tell me here?
Taking half.
Okay. How would you write that without those words, Ginny? I like what you said.
Wouldn't it be n? I don't know. It's n something 1/2. I'm not sure.
Yeah, and that's what's a little tricky, and that's why we want to make sure that when we are doing this, we're not unsure. If we're explaining it to somebody, we want to make sure that they're positive as well, which is why we said only multiplying. Because if one's multiplying, one's dividing, and we say, well, you multiply this one by 2 and you divide this one by 2. Well, remember here, it was D equals positive 2, or it was D equals negative 2, and it was obvious. We added 2 each time, or we subtracted 2 each time. But here, now you're going to need a whole word to tell me whether it's multiplying or dividing. And we don't like words in math. We like symbols. Okay? So that's why we are going to say there is a common ratio. Common meaning for every single one of these. And ratio so that we can always multiply. So what would that common ratio be for this one? It would be 2. We would multiply each and every one of those by 2. But what would it be for this one then? What would we multiply by? How would we say dividing by 2? Multiplying by what?
1/2.
Very good. Now there's no confusion. Does that make sense? That's why we're going to say it's only multiplying. Go ahead, Jenny.
For this, we have to put R equals. If we put D equals, it would be wrong.
Exactly. Because what does D represent?
That is like plus or minus a constant.
Good.
Yeah.
Is there a difference if we wanted to know our age gap, right? We would take mine and subtract yours because obviously mine's older, so it'd be positive, right? But is there a constant difference between these? No, here it's +1, here it's +2, here it's +4, here it's +8. You can see, no, there is a difference, pun intended, between that and that, which is why we use a different letter for each.
Gotcha.
Okay, good point. And so if they tell us this, then we know there's that. If they tell us this, then we now know it's that. And so when they say geometric, you know, how am I getting from one to the next? Multiplying by some ratio. If they say arithmetic, then you're going to use probably how you said this before I said it, arithmetic. Adding or subtracting to get from one to the next by some common or same thing. Okay, so that's what this is saying. How do we get from one to the next? Well, we would multiply by our r. To get from the first term to the second term, we'd multiply by the r once. If we wanted to do it again to get to the third term, we would have had to have multiplied by another r, and then another r, and another, and another, and another. So what do you think that we are going to want to be able to write? Well, of course, that formula, that general rule for us to be able to figure out, what does this stand for?
Any number?
Any term, any number, that's right. I want to know the nth term. Well, you can see right here that this is obviously the first, this would be the second, third, fourth, all the way on to the nth. And what would we need to know in order to find it? What would be nice to know in order to find the 10th, the 12th, the 127th term?
The first term on the ratio?
Very good, Alan. Let's find the first term. If they tell us where to start, beautiful. And then what would we do with that ratio, Alan? Everyone? If we knew the first term and I told you how to get from one to the next.
Well, you can manually do it like half, 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 or you can use the formula.
Very good. And that's what I'm trying to help you guys to discover. What is the formula? Because as Alan mentioned, manually, if I want you to find the 121st term, no, I'm not going to multiply by a half that many times or two that many times. Some of you probably will, which is why I have to put big numbers, because if I just put A7, then yeah, you could just sit there and multiply it out a few times. But our goal is to learn and broaden our horizon, not just sit there, calculator, times 2, times 2, times 2, right? We're looking at bigger ideas, making this thing work out a little bit more. So if we have the first one, look, Alan, how many times would I have to multiply by that ratio, that r, to get to my second term?
Once.
Very good. How many times would I had to have done it to get to my third term?
Twice.
You guys seen a pattern yet?
n-1.
Very good. So I would have to multiply by that common ratio, that factor of 2 or 1/2 or whatever it might be, n-1 times. Does everybody understand why it's n-1? Because we start with that first term and we don't have to multiply by that r until we get to the second. Very good. Excellent. So we just came up with this without me just flat out giving it to you. But in case you didn't have it written down, I wanted to make sure that you had it there. Okay, so this is the formula. But I much rather you guys write it the way that I did. Because what do people start making mistakes with? They will multiply these two things and then do the exponent. No, 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 no. Be careful. Order of operations, right? Parentheses, exponents, multiply or divide, add or subtract. Okay, these four things in that order. Okay, be careful with that. If you want to write it down, I suggest you at least, at the bare minimum, put parentheses around that R, the thing that has the exponent with it. Preferably both. Okay, so that's pretty much it for that first section. All right. I just have a couple of examples that I'd like you guys to do before we move on to the next. What's the key words in this first example?
Geometric sequence.
Very good. That tells us that we're going to do what to get from one to the next?
Multiply.
Which means I know right then and there, I can use this formula, this equation. And by the way, how many unknowns are there in this one equation?
3.
2.
1, 2, 3. Does everybody agree?
Yeah.
Oh, yeah, we don't have a 1.
There's
Yes.
actually 4.
Oh, dang.
Yeah, because a sub n as a whole stands for the nth term. So there's technically the a sub n, the a1, the r, those are the obvious two, and then the n itself by itself. And remember, what's the secret sauce to cooking math? I said math.
1 variable, 1 equation.
Very good. If we can get it down, if we know 3 of those things, then we can find the one that they want us to know. Very good, Jenny. I think I've said that enough that you guys have it down. So as Alan mentioned, notice they gave us the second term and the third term. So I'm going to explain this obviously, but I'm also going to explain what would happen if this was, say, the fifth term. Now this example is a little bit nicer because we have the second and the third term, which means if we can figure out, because they told us it's geometric, what that common ratio is to get from there to there, then we're almost done. Because remember, the only two things we need to find any term is, which that means they told us this, was A1 and R. We would have those two things, we would have this, and we'd be able to find the nth term then. And what are they asking us for?
A6.
Which means I need to know that first term, the R, and I already know what?
The different, the n term and the difference between A2 and A, not the difference, the ratio between A2 and A3.
Good correction. Very good, Alan. Because these are consecutive terms, I know because they told me it's geometric, it's not going to be a common difference. I'm not going to figure out what the difference between those are and take 32 minus 4 to find the D. I'm actually going to take the ratio, which is if you know any term, divide it by the one before it, and that'll tell you how you got from there to there. Because remember, we said it's multiplying, so that's why we do the inverse and divide. But you can see, to get from there to there, the second term to the third term, we would do what?
Divide the second term by the previous term.
Which I don't know the previous term, but I do know the third term, so
Yeah.
I'll divide it by the or 4 times what gives you 32, gang?
8.
Yeah, I mean, that's pretty easy. A lot of you are putting it in the chat. Very good. So that goes where again?
R.
For our R. Very good. So the 8 would go there. All we would then have to do is, well, because it's so close, we can kind of just reason with this one, right? If this is A2 and this is A3, and this was a 4 and this was a 32, we said that we would multiply by 8. If we're going left to right, well, then we can just do the inverse to go the other direction. Reverse it, right? Inverse. So divide this by 8, we get this. Divide that by 8, we get what?
One half.
Yeah. Which gives us what, Alan?
1/2.
which gives us what though? What does that represent?
Oh, A1, sorry.
It's all right. Just making sure you saw it. That was the other thing we needed. And quick, guys, what's half of 8?
4.
I don't care.
Oh, no.
Why don't I care? Because remember, I warned you. This is what a lot of people do. And that's why I said quick. Because when you're rushing, you make mistakes. Right? Even though these are right next to each other and you know it means to multiply, you have to do the exponents first. All right. So again, just be careful with that. And then rewrite this as a 5, punch that in your calculator, take half of it, and there's your 6th term. Okay. Now remember, when you multiply over and over and over again, especially by a large number like 8, things are going to get pretty big pretty quick. So unfortunately, you're going to have to use your calculator quite frequently in this section compared to the last, with the arithmetic a little bit slower paced when we add or subtract the same number a bunch of times. Okay. All good with that? Anybody get the answer?
16,384.
Is that right?
Mhm.
8 to the 5th, you can see up there is 32,768. Divide it by 2 or take half of it, you get that 16,384. Big number for only the 6th term in this thing that started at 1/2, went to 4, went to 32. Again, see how large these grow and how quick. Got to be able to use the formulas in this. Doing this by hand or manually, like Alan said, it's going to get messy, like Lionel. All right. Now, what about this one? No soccer fans out there. Okay. This one wants us to, if they give us a sequence, a list of numbers, they want us to write that formula. And what are the only 2 things I need?
R and the first term.
That's it.
Yeah.
They definitely gave us the first term. What do we need?
This is a difference. So no, it's multiplying. Sorry, it's a ratio.
Why do
so-
you know that? Why do you know that, Alan?
Because there's not a consistent difference from the first to second to third.
And they told you.
Oh, and they told us, yeah.
But yeah, you're absolutely right. You should see it. And what else you should see is that my signs alternate. And if your signs are ever alternating, what does that mean we had to multiply by?
Negative.
And that means we could not have added or subtracted by the same thing. So whenever you see these alternating, you know it has the opportunity to be geometric, cannot be arithmetic.
Wasn't a question like that on the group quiz? Yeah, I had to look that one up. That one was hard.
We had a negative that we had to throw in front, and it was in plus or in -1. It actually does not matter. And then you had to multiply by, it was doubling each time.
Yeah, I had to go on NetTutor for that one.
I'm glad you didn't give up. Once you saw it though, wasn't it pretty obvious? And that's where it gets a little frustrating, right? It's like, wait a minute, what is the common? Well, some of these things are just patterns to them, but they aren't arithmetic or geometric.
My problem is creating the actual formula, because it's like seeing the pattern is nothing, but you're asking for the formula. So it's like, well, shit, I can't just sit there and, say, hey, I know the first term. I got to give you the formula and then the first term.
Right. Yeah. And that's a good point. And there's another one that there was right, I think after that one, Jenny, on the group quiz. And it was, I think 1, maybe it even started with 1 and then 1/4 and then 1/9 and then 1/16, 1/25 and so on. And so that was the pattern of, obviously the top wasn't changing, but the bottoms were just squares. Right. So again, to see the pattern is very fun. And I actually, if we were in class, I'd actually give you guys some fun ones that are very, very tricky. but it just really gets you guys' minds working. All right. One of them was from a 7th grade gal that actually had a brother that was going through, and this is when I was just doing my student teaching. And she was in there and she's like, my brother's a math major and he gave me this problem. And I was like, oh, that's a good one. And so I've always remembered it, but maybe at the end, I'll throw those fun ones out for you guys. All right. So for this, we have our A1. And we obviously can see what the R would be. And for that, doesn't get any easier, Dustin, right? Don't really have to simplify and do the things that you had to do with the arithmetic. For this one, the only time you will ever be able to simplify is when your A1 is the same as your R. Because remember, when the bases are the same, we can add the exponents. But even then, I'd be fine with you leaving it because then you can see that you know and found what you're supposed to. Okay. Remember, the power of these formulas, though, is that this right here allows us to find the nth term quickly without having to do, as mentioned previously, manually with a lot of labor, multiplying by -3 until we got to the one they wanted. Okay. That's it for this section. Of course, there can be more challenging ones. Instead of giving you the 2nd and 3rd term, I could make it the 2nd and 13th term, which then means you're going to have to use this formula and you're going to have to use it twice. But that's okay, because even though we'd have the nth term and the n, we would still have these two unknowns. And to Jenny's point earlier, we only know how to solve one equation with one variable. Well, now we would have 2 variables, which means we would need 2 equations, which is fine because they would have given us 2. It's just going to be more work to find that A1 and that R. Okay, but nothing that we haven't done in this unit already. All right, 3.4 here. We got series now. And for all you baseball fans, there's quite a few of them going on. Oh, poor Giants. Got robbed. No, they were probably going to lose, but they shouldn't have lost that way. What is a series versus a sequence? We know a sequence is a list of numbers. Well, a series, whether it's the divisional that's going on right now, national and American, or when they get to the World Series, what are they obviously trying to do each and every game? Win. But does that mean they win the series? No. What do they have to do in order to win a series? Do they have to win 2 in a row? Or 3 in a row? No, it's just the collective sum. And Bernice put a total of 3. That was last series. To get to the divisional, it was best of 5. So they had to win a total of 3. It didn't have to be 3 in a row, though. So that's what we mean by series. In this, it is going to be the term sum, where a sequence was a list of numbers. Okay, so I will go ahead and fill in a few of these blanks with you to make sure that you guys understand some of the terminology within this. I would like to call it the last section of this because the next one kind of goes off onto a tangent. Okay. We're going to explore how to find that sum of those series, but there's going to be several different types of series. And this might blow some of your minds, okay? The first blank we're going to put in here is what is called a, how would you say that?
Finite.
Very good. What if it's not finite?
Infinite.
Very good. We put infinite. And you guys know what infinite means. It means this many, right? We even have a symbol for it. We're actually going to get to those too. You know, if I give you a list, a sequence of numbers, and it ends, I say find the first 10 and add them up, then you know you'll take those 10, you'll add them up, and you'll give me an answer. But what if I asked you to find an infinite sum? Where does that end?
Nowhere. Wherever.
That's right. So I'll get you to think about that a little bit later, but I wanted to already plant that seed. Okay. So if it's not infinite, that's like a double negative, and a double negative in math, we know that we can make a positive. So that's what we mean by finite, is not infinite, and therefore it ends. Okay. And what we like to call those, the fancy math terminology, is the nth partial sum. Because if I gave you the rest of the day, you would be able to add another number, add another number, add a number, or multiply, 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 and continue on until you got bored or tired. That's infinite. So what we want to be able to do is find the sum of a part of the sequence. How many? N many. So that's why we call it the nth partial sum. That's a mouthful, but I want to make sure that you guys understand when they say that, what that means. And as I mentioned to you already, we're also going to find the sum of, and this is a little crazy, an infinite or an infinite series. Now, how? I want you all to take 60 seconds and work that brain out real quick and think to yourself how we might be able to, and more importantly, when we might be able to find the sum of an infinite amount of numbers. All right. Anybody come up with anything? When do you think we might be able to add an infinite series or sequence of numbers?
Will there be like some boundary or restriction to it?
Very good. I like that, Jenny. Some people are putting some stuff in the chat as well. Any others? Somebody was saying, make it into an equation. That's getting a little bit more detailed as far as how we might be able to do it. But my bigger question is, when will we be able to do it? And Jenny kind of mentioned something. You know what? I'm going to leave you guys on the edge of your seats. I'm going to come back to this. All right. Keep your attention. I'll mention that in a minute. Gavin, very good. I'll mention about that in a little bit. Okay. He put something in the chat. All right. So some more things we need to talk about is what these things look like. All right. And when we write that series or sum, we will oftentimes write it as a capital letter S. Okay. For series or sum, we're going to add that up. Now, the problem is sequence also starts with S, right? But for a series, we know the English letter S can represent the sum or series of these, but because this is used for both that and that, to be more obvious, we're going to use the Greek letter. And does anybody know the capital letter S in the Greek alphabet? It is actually this E-looking shape, which is actually called, what is it?
Sigma, I think.
Yeah, very good. Sigma. This is the capital letter S in Greek. Okay, it still means the sum. We're just going to use this to denote that I want you to find that sum of that series. right? A lot of you guys knew that one. Very good. Okay. This is actually called summation notation, for lack of a better term. Okay. Not a big deal. Just wanted to make sure that you know that. All right. And they're going to therefore have to tell us, if they're asking us to find that big letter S, that big sum, they're going to have to tell us of what, right? How many things and how to find those things, which is that formula, either for arithmetic or geometric. Okay. So this is what they usually will look like. That Greek letter S. The thing in front of it is going to tell us how to find each and every one of those terms. And as you guys know, we always in life start at the bottom and work our way up. And that bottom thing is going to tell us how we start, or where we start, by plugging into this. And we will plug in everything all the way on up to what they call that upper limit. So in this case, we'd be plugging in for A1, A2, 3, 4, and 5. From 1 to 5, we'd be plugging into that. So we'd obviously get 2 first, then a 2 times 2, which would be 4. And you guys can see the pattern. It's multiplying by 2 to each thing. So then this one would be 2 times 3, 2 times 4, 2 times 5. And we would be tasked with adding all of these up. So take the 2 and the 8, that's a 10, that's a 10, and that's a 10. Our answer would just be 30. It's that simple. When we're only tasked with finding the sum of 5 things, right? What are we going to try to learn how to do? Find the sum of 150 things. And do I want, yeah, Alan, do I want to find all 150 things and then add all 150 things? No. And luckily for you guys, you don't have to. Okay. But again, recognize and know what the thing in the front, what the thing on the bottom and the top represent. Okay. This one is a little bit more, I think, explanatory than that definition that the book gives you. Luckily for you, a 7-year-old figured out a shortcut. Did that catch your attention? Are you smarter than a first grader? No, not this one. Okay. This guy, his name's Friedrich Gauss, German mathematician. At the age of 7, his instructor, his teacher back then, didn't want to work. He said, you know what, class? Add up the numbers 1 to 100. And what did most of the class start doing? Even though Nike wasn't even around back then.
Just do it.
Yep. They just sat there and started. Now, mind you, they don't have calculators back then. Okay. Their tablets were of stone and they etched in them. Okay. They were unlike ours. Okay. There was no Wi-Fi in that area. Okay. So if I was to sit here and do this, you know, that's going to take 7-year-olds quite some time. Teacher thought he bought himself the morning to sip on his coffee, kick his feet up on his desk, read the paper. But unfortunately, a few minutes later, little Freddie Gauss walked up, handed them paper, dropped his pencil, and walked out. No, I don't know about that last part, but he definitely brought it up a few minutes later. All right. And again, to Dustin's point earlier, he just found a pattern. He didn't need a formula. Eventually, he came up with one. Anybody have an idea of what we might be able to do rather than doing that's 3 plus 3 is 6, that's 4, that's 10, and then 15, and then 21, and
Opposite numbers on the line, add them. So you have you basically have 101, or you do 100 times whatever.
that's right. He said, you know what? I'm not going to just go left to right. I'm not going to be like everyone else and just go right down the line. He said, I'm going to go against the grain, like my guy Dustin over here. He said, you know what? I'm going to take the first I'm going to start in the ends. And I know that those two add to be 101. And then I'm just going to go to the next two in line, because what do I notice that is?
101.
And then the next two. And the next two. What does it look like we're getting? A bunch of times.
101.
Dalmatians, that's right. How many times would we have that 101?
50.
You know that this is the first term, this is the second term, this is the third term. So you can see the pattern here. This therefore would be the 100th term, 99th term, and so on. And since he was able to pair them up, and there was 100 terms, he knew that he would have 101 50 times. Now that's still impressive to be able to do multiplication, right? But if you break down 50, you just got 101 times 5 times 10. And you can do 101 times 5 easily, right? That's 505. And then you can also multiply by 10 easily. You just add that 0, you move the decimal over one place. And that's how he walked up and said, I'm probably not going to learn much from you. I'm out of here. Pretty impressive at the age of 7. Somebody put in the chat that Gauss was a cheater. Age of 7, he went on to do many, many things. He's one guy that I learned to despise because he did so much. And as I went through my math bachelor's and master's, I got to see many of his other discoveries that were just very, very ingenious, right? So again, it pays to think outside of the box because that is a heck of a lot faster than simply doing this in order. So.
Oh, I saw him in biology. Sorry.
You good? The cool thing is we know that this sequence is what kind?
Arithmetic.
And therefore, all he had to do was prove that it works for any arithmetic. And of course he did. And here it is. So what this says is to find the sum of any number of things, all you need to know is the number of things that you have and the first and last term. Now notice the whole thing is divided by 2. I'm going to tell you right now, that's where most people make mistakes on this. Because what he did, Gauss, was he took the first and the last and he added those together. The A1 and the A sub n, the 100th term, right? He added those together. Then he took the number of things and he divided that by 2. And then he multiplied them together. But here's the problem. What if the teacher said instead of up to 100, he said add the numbers 1 through 99?
Odd. Yeah.
Well, now it's odd, and that's not going to work out as good. But if you would have taken 1 and 99 and added those, and then 2 and 98 and added those, you see that pattern still works. You get 100 each time. So that's why instead of just putting it over this, sometimes it's better to multiply it across and say that we could have the whole thing over 2. But what I'm going to warn you about with doing that is that does not mean you divide it into this and that. Okay, one or the other, because these are multiplied together. All right, so if you want to maybe alleviate a mistake and you don't want to put it there, my suggestion is to put it in front. Because then you can see you got these two added together times this times a half. And now you know that that half can either be to this or that sum, but not both. Okay, that just happens to be where most people make mistakes. All right. Pretty cool, because what does that mean? We don't have to be too creative. We just need to know that it is what kind of sum. Has to be what?
Arithmetic.
Arithmetic. Very good. All right. If it is, then you can use this formula. And of course, since there's one for arithmetic, there's also one for geometric. Okay, the problem is, you know, in order to multiply to get from the one to the next to the next to the next, that's more challenging. Well, so is that formula. All right. So that one doesn't have as cool of a background story, but here it is. And again, as long as it is geometric, then you can use this. Right? But there are some restrictions and some important things that you have to be able to use. One is your R can't be 1. Which makes sense, by the way. If R is 1, what would your series look like? Right? So that's one reason why. The other is if we put a 1 in down here, we get a 0, and we know we can't divide by 0. Okay? Now, again, one mistake that a lot of students make with this formula, which is the sum of n things, you still need to know the first, but you also need to know R. And if you notice, this is 1 minus R to the n. This is 1 minus R. It is not 1 minus R to the nth power. The R is the only thing that has the n. If it were that, then you would have been able to cancel one of these with one of those, and you would have had one less. Okay, so please don't cancel these things. It is A1 times 1 minus the R to the nth over 1 minus the R. And unfortunately, what does R stand for?
Ratio?
And if R is a ratio that makes your numbers get smaller, it means it's a fraction. And unfortunately, if this is a fraction and that's a fraction, already in our big fraction, yeah, these get messy. Okay, so again, be careful with it, but have those written down, make sure that you know how to use them. Okay? So here's the cool part. I did tell you earlier that we're going to be able to find an infinite sum. This so far was find the sum of a certain number of things. Find the sum of a certain number of things, depending on if it's arithmetic or geometric. And by the way, guys, if you forget for some reason which one is which, how should you know that this is what? And this is therefore what? Arithmetic or geometric?
Well, the R is going to be there for geometric.
So you know this one is the geometric, and therefore this is
Arithmetic. Yeah.
arithmetic. Okay, excellent. And that's why I gave you that little background history lesson, so that you hopefully would remember that one. Okay. How are we going to find an infinite series? Well, that means change all the n's to infinity. And I asked you guys earlier a question. I gave you 60 seconds to pause and think. When are we going to be able to do this? Well, if my numbers are doubling each time, right? I start with 1, I go to 2, 4, 8, just keeping it simple. What's going to continue to happen to these things?
Grow larger. Double, but yeah.
When is it going to stop, Alan?
Never.
So the number would be infinite, or
Very good. If we were to put something, we would say, well, it just goes to infinity. Remember, these are some of the limits that we were talking about. But that's not good. What is the sum? A lot. Well, there is a way that we can actually give a number. And that is What if I gave you this example here? I don't want to give you too much info yet, so I'm blowing this up. What if I asked you to add this up? Could you guys add the first few things? 10, 15 and a half. Then what? Give me the next few. What's the pattern? What's the R?
1/8, one, or it's one, the R is 1/2, but the next would be 1/8, 1/16, 1/32.
A 64th. Very good, very good, very good. What do you notice that those are trending towards? Alan said earlier infinity because they just kept getting bigger and bigger and bigger.
0.
0.
Now these are kind of like that asymptote that we were talking about on many of those graphs that we dealt with. Very good. Which means eventually, it's pretty close already, right? But as Dustin was mentioning, then we'd have 1/64th, 1/128th, 256. These are getting really, really, really small. And what happens when we add something really, really, really big? Gets bigger and bigger and bigger. But what happens when we start adding something that's approaching 0? What happens when we add nothing? Nothing happens. That's right. So the only time that we can actually add an infinite amount of things is when this is approaching 0. And when will that happen? When our R is less than 1, as Gavin put in the chat quite some time ago. Very good. Now remember, what about the negatives? Would that be okay too, to throw in a negative? Well, yes, it actually has to be where the absolute value, which means take away whether it's positive or negative, that value of R is less than 1, which means that our R has to also be greater than -1. We have that little void on our number line between -1 and 1. And what are all the numbers in between -1 and 1? What do they look like? What kinds of things? Give me one word.
Infinite.
Good, good, good. But what kind are they? I'm not saying how many are there, Jenny, but you're right. What kind of things are between -1 and 1?
0, 0 in the middle.
Good. But what kinds of things are between 0 and 1? And 0 and
Fractions. Oh, fractions.
Very good. So if you see your R, that is a fraction. Now, careful. I can try to fool you. I can test you. Just because it's a fraction doesn't mean it's smaller than 1 for my ratio. Because what is 3/2 actually?
1 and 1/2.
Yeah, it's going to grow by a little, but it's still going to grow. And if we're going to infinity, it's going to continue to get bigger. So we said if we added these things up, we know that we can do these. That was our 10, 15 and a half. If I wanted to add the next thing, what would I have to get? Common denominator.
Oh, common denominator.
Right? That wasn't a trick question, gang. All right. So now I got 15 and 2/4, and I add 1/4 and I get 15 and 3/4. Then I would have to do what next? I added the 1/4. Now I'm going to have to add the next term, the 1/8. So now I'm going to add an 1/8 to that, which means what do I have to do?
The common denominator again.
7/8.
Ooh. Now I got 6/8 plus 1, 7/8. What about the next one?
15 and 15/16.
How'd you get that so quick?
Because there's a pattern.
Very good. If you haven't noticed, guys, that's what this whole unit, or at least this chapter, has been about. Patterns, right? What would the next one be? Quick, Dustin.
31/32.
What about the next one?
63/64.
Very good. And so on. What are we getting closer and closer and closer to with these fractional parts? Which means if you were to say that this goes on forever, it's going to get so close to 1. Because we already have the 15, we know this is going to approach 1. We're going to say the sum of this is actually equal to what?
16, approximately.
Okay, I like that. If we're talking limits, it's like it would approach 16, right? But remember, this goes on forever. And it's going to get so close to 16, we're going to actually say that the limit is 16. Now, let me go back and show you why this all works and give you the formula so that you don't have to reason yourself through it every single time and look for patterns. Let's go back to this, where we said that this n would go to infinity. And remember, we said that our r had to be a fraction, right, Alan? And do you remember what happened when we had a fraction like 1/2 raised to a really, really big number? What would happen to the 1?
1.
Good.
I mean,
What would happen to the 2?
it would 4, 8, 16. Yeah, it would go up to like infinity.
Good. It would be really, really, really big. We just put this. And what do we say 1 over a really, really, really big number approached?
0.
Which means this whole piece just goes away. It becomes a 0. Which means the only thing left is a1 times 1 over the 1 minus r. And if you guys notice, that's exactly the formula that we get to use. Which is crazy that an infinite geometric series to add up an infinite amount of things is actually easier than adding up a certain number of things. That's crazy, isn't it? Look at this one. And look at that one. Way nicer. Okay, so make sure that you have that written down. And remember the caveat. The only way that that works is if your r is a fraction less than 1. Now let's go back and use it and see if it gives us our 16 that we said we'd get. You guys ready? S equals a1 over 1 minus r. We still need to know those two things again, Alan. The a1 and the r like we did at the very beginning. What's a1?
3? No.
8.
8, right? That's our first thing here. Sorry, I know I butchered it. All right. It's an 8. And what did we come up with? What did we say the r would be?
1/2.
Very good, which goes down here. So we get 8 divided by 1 minus a half, which is a half. And do we like dividing by fractions? No, so instead we'll multiply by its reciprocal, which remember means I have to do it to both top and bottom. I got to multiply by that fancy 1 to keep what I have. But the reason we did this was so that the 2's would cancel out and we get the same thing we reasoned to get. Pretty awesome, right? Look how much work we had to do to get there, rather than all the reasoning that we had to kind of talk our way through. Pretty phenomenal stuff. That's it for that section. Hopefully your mind is blown that we're actually able to add an infinite amount of things, and it's that simple. All right, then. On to the last section, which kind of takes a step away from all this, but it is related, and you guys will see why in just a minute. Okay. This is called the binomial theorem, which I'm not even going to teach you. I know it seems kind of weird, right, to even mention that. I'm not going to actually go over the binomial theorem because I think it's more work than it's worth. I'm going to show you one way called Pascal's triangle, and then I'm going to show you an adaptation of the binomial theorem. So I'm still going to show it to you, but not all in its glory. I'm just going to take the key parts from it. Okay, show you how to use the parts that you need. So what is a binomial? Bi meaning two, nomial meaning names or terms. Okay, so a binomial is when we have an A plus or A minus a B. Now remember, this can be anything, this can be anything. So an expansion meaning, what do we do when we have it to a power? Well, you guys all know what anything to the 0 power is. What's that?
One.
Good. So that gives me a 1. And what is anything to the first power?
Itself, or what you originally had.
Good. And have we done a plus b squared enough that you can just tell me what that's equal to? Do I just get to square each piece? No, very good. Remember, that means a plus b times a plus b, which if we distribute twice, we get a squared.
Plus 2ab.
Very
Plus
good.
AB. No, b squares are.
A squared, an AB, another AB, which is where the two ABs came from, and then a B squared. Now, guys, if I wanted to do that again, I'd have to take this and then multiply it by what?
One more a plus b.
To get my third multiple of it. Which means all I'd have to do to this is multiply it by an A and then a B. And if I multiply the entire thing by an A, that, and that will all have another A, won't it? Which means I now have an A cubed, 2a squared B plus an AB squared. Just multiplied all of that by an A. Then I'm going to have to take these things and multiply it all by a B now, which is going to give me 2ab squareds. So I'm going to put that over here, lining it up. Then I'm going to have, actually, I should write it better. Let me just write it so it stays, huh? Gives me an a cubed 2a squared b plus an ab squared. And then if I multiply by another b to all of these, I would have my a squared b, 2a, and then a b squared, and then a b cubed. So notice this one, I have an a cubed, 3 a squared b's, 3 ab squareds, and a b cubed. Have we started to see more patterns? Because so did a fella by the name of Blaise Pascal. Pretty awesome name, French fella. I actually wanted to name one of my kids Blaise, but my wife didn't like that, right?
That name could be interpreted like another way.
Yes, it can. He even spelled it kind of cool. Blaise Pascal is known for what is called Pascal's triangle. And you guys remember, patterns are all around us. And what he discovered was that this one would be a to the 4th, and then a cubed b, a squared b squared, ab cubed, and b to the fourth. But all we had to do was figure out what the coefficients were. And if you notice that each one of these has a 1 on the outsides. 1, 1, 1, 1. 1, 1, 1, 1. But how are we going to find these other ones on the inside without doing all of this again? No, thank you. Well, what he noticed was that there's also a pattern. And it's a whole lot easier to see if you get rid of all those A's and those B's. Let's get rid of all the variables. Have we done this a few times already in this class? First, we did it with synthetic division. Then we did it with the matrices stuff. Now we're doing it again because it's easier to see the things that are being affected. So what I'm going to do is I'm going to grab all these and just the coefficients. And then this was a 1, 2, 1. This was a 1, 3, 3, 1. Now, can you start to see some patterns a little bit better? Dustin, you were about to say something?
Oh, it's just the coefficient just go on the inside is just going to be what your power is.
Okay. So he noticed that this was to the first, and then the next one over was to the first. This one was to the second. The next one over was to the second, to the third. So the next one over would have to be to the fourth.
It's also the sum of the what your powers are on the inside too. So you got a to the third, b to the first, a to the second, b to the second, a to the first, b to the third.
Very good. He's pretty good at finding patterns. I like that, Dustin. Excellent job. Some of you have done this before. Great. Now, there's all kinds of patterns within this, right? But the way that we find all of the insides, which is the best part of our cake, with all of our candles on the outside, these ones, is by adding them up. And you can see if I took these two and added them, I get the 2. If I take these two, I get a 3. 3. These two gives me the 4. So what would be the next thing? And there it is. So what if I wanted to take this out to the 5th? As Dustin mentioned, I can take these A's and B's and I can do that pattern, but then I can also find the coefficients by using Pascal's triangle. I know the outsides will be 1s. What's going to be the next in my line from left to right?
Five, 10, 10, and 5.
Also, hopefully you're noticing, very good, Jenny, that there is not only a pattern with how we find these things, but it's also symmetrical. See how the right side and the left side are symmetrical? Pretty cool. Now, also notice one thing. How many terms do we have? Say it was to the 3rd power. How many terms did we end up having?
One more term.
Very good. There's always, for 4, 1, 2, 3, 4, 5. And as Dustin mentioned, if I wanted to find the 5th, I just look 1 to the left. And again, there's all kinds of patterns. Look down this row. 1, 2, 3, 4, 5. Look down this next diagonal here. Add 2, add 3, add 4. So people have blown this up and it looks like the back of my wall here. And they've tried to find other uses for this. The only thing that we're going to use this for are the binomial expansions. Okay. So that's pretty much it for this. I'm going to do an example with you real quick. then I'm going to explain how else we can find those coefficients by using the binomial theorem. And that's it. Okay. So what am I going to start by doing? What would be nice to know? If they want me to do x plus y to the 6th, am I going to sit here and do x plus y times x plus y times x plus y 6 times? Should we be able to, Ellen? Do we want to? That's why we're learning this technique, okay? By either Pascal's triangle or the binomial expansion. And when I was teaching this in high school and all the way on up to college when we go over it, I always would ask for one person to race me. And I would have a student try to do this while I slowly go through and explain it just like I would now and set it up. And I usually beat them every single time. And if I don't beat them, they usually make a mistake somewhere. Because you can imagine doing this out 6 times that you're gonna make a mistake somewhere with the coefficient or your exponents. Okay? So let's start with how many terms we're gonna end up having. How many we're gonna end up having if it's to the 6th power?
7.
Then I'm gonna draw 7 blanks. Too big. And what do I know each and every one of those are going to have in them, Dustin?
6th power.
Good. But just like all the other ones, they all had a bunch of A's and B's in them, didn't they? Well, then, before I get to the powers, I'm going to write down they're all going to have X's and Y's in them.
Are you gonna have x, xy, 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 y?
Good. And what I'm going to do is I'm just going to write both, and you'll see why in a minute. Because then the next thing I want to do is figure out what the powers are of each one of these things. And we know if we took this and rewrote it as x plus y times x plus y 6 times, what would be in the first slot?
X to the 6th.
That's right.
Why is there a y though?
Okay, good question, Alan. I'll get to that. I'll show you why in a second. No pun intended. Okay. But I know that if I multiplied this all out on the far left, I would have 6 x's. Right?
And
And
because
what
the y has,
other pattern did we notice? Sorry, Dustin?
I was just saying, because the y has no power, it's just 1.
No power. That's right. Very good.
Oh, okay.
Because as he mentioned earlier, he saw a pattern when I didn't have the clutter of the x or the coefficients in front. He noticed that since this was to the 4th, look, 4, 4, 4, 4. This was to the 3rd, look, 3, 3, 3, 3, 2, 2, 2, and obviously 1. Yeah, all kinds of patterns within this. So I know right here that because it's on the left, it's going to start with the 6. Then what is it going to do as we move on down?
Go down 1 until it hits the middle.
Just as Dustin mentioned. 6, 5, 4, 3, 2, 1, 0. And because we have those, we know that the sum of these all have to add up, or because that was left to right, we started on the left for the one on the left. We can start on the right for the one on the right and do the exact same thing. 6, 5, 4, 3, 2, 1, 0. And Alan, as you mentioned, there shouldn't be a y there, but we know anything to the 0 power is
1.
Now the only thing we have left to do is find the coefficients for all of these, clean this mess up, and give them the answer. Like that. Rather than actually foiling, distributing this whole thing out, combining like terms, doing it again, and then doing it again, and no, thank you. So that means, what do I know is always going to be on my ends?
1.
Then do I actually need to find those? Or can I just put those? Yeah, I'm going to just put them. And then what else? What other pattern did we notice? What is the second thing always going to be? Dustin saw that one earlier, right? First power, next thing was 1. Second power, next thing was a 2. Third power, 3. Fourth power would have been a 4. And we saw that right here. 1, 2, 3, 4, 5. So we know ours is going to be a what?
6.
There, and because we know it's symmetrical, there. And whatever this one is going to be the same as that. And then this one will be all by its lonesome. But here's the problem, guys. Here's the bad part about Pascal's triangle. If this were the first problem that I had on my assignment, what would I have to do to find all of those coefficients? I would have to have done all of that just to find that next row. You have to do all of this just to find the one that you want. And in reality, do we need all of them? No, we only need these 3. So that's where the binomial theorem comes in. So I'm going to give that adaptation to you right now just to find the coefficients. That's the only part I use of the binomial. Okay. It has a bunch of other stuff in it, but I'm going to do this before I actually find these with you, just to show you that you get the same thing. Go ahead, Dust.
Oh, it only works for this one. It doesn't work for the previous ones, but I was just noticing that the sum of the outsides equal the next one. Unfortunately, it doesn't work for all of them.
Got it.
So you got the 1, 6, 6, 1, it's 14. But that's not.
I like it. I like it. So guys, check this out. Here's how you use the binomial theorem adaptation, okay? So I'm going to put a little asterisk by the binomial theorem because this is not the whole thing. We're going to only use the part to find the coefficients. You will take whatever the original power is, and you will divide that factorial by whatever the other 2 exponents are. So let me make that make sense. What do we have? Well, it's to the 6th power. So what is every one of these going to start with on top? That will be our n factorial. So we will start with 6 factorial on top of each of these. Then here comes the easy part. How do I know what these 2 things are going to be? It's whatever the exponents of the term is. So we take the exponent of the original thing and divide it by the 2 smaller ones that is for that term. And haven't we already done things like this last week? What would I do with this? This.
Expand them out. I don't know the better term to say it.
Yeah,
And
no,
then-
that's exactly right. But I definitely would not do that. Because if you expand it out, then it's going to be a lot bigger. I would just start doing the canceling because I know what happens when I expand it out. I know what 6 factorial means. It means 6 times 5 times 4 times 3 times 2 times 1. And I know what 4 factorial means. It means 4 times 3 times 2 times 1. So like you said, you'll be able to take all of these and make them ones. So just do it. Don't expand it out. Don't need to.
30 over 2, 15.
So the 4, 3, 2, 1 is going to cancel with the 4, 3, 2, 1. So I just have 6 times 5 over the 2 times 1, which, as you mentioned, you can do 30 over 2 or cancel and get 3 times 5. And by the way, since this and this are the same, I wouldn't have even done this. But do you guys see that this and this are already set up the exact same way? It's just this is a 4 and a 2, and this is a 2 and a 4. But because they're multiplying, order doesn't matter. You guys see that? So this becomes a what?
X squared y to the 4th.
That's it. That's what the
Other's opposite.
1, 2, 3, 4, 5th term would be. All right. How about this one? What would it be? Just for good measure.
630 times 4, 120.
6, 5, 4. This would be a 3 times 2. So that would cancel with that. So we just get 20. Guys, check it out. 1, 6, 15, 20, 15, 6, 1. It's exactly what we got. Do you see it? 1, 6, 15, 20, 15, 6, 1. But what did we not have to do with this binomial theorem?
Everything that's in between.
We didn't have to do all of this just to get that.
That could have been shorter though still.
Could have been if I didn't have to sit here and explain to you guys how to do that. But Alan, in reality, we only did this and that, and we were done. Because this and this are the same. And we knew all of these and we knew all of those. So I agree with you though, Alan. Which way do I want you to do? I don't care. Whatever way you understand. But what I don't want you to do is only know one way. Because guess what, Alan? And everyone, although you give me this as your final answer, x to the 6 plus 6x to the 5th y plus 15x to the 4th y squared.
Doesn't show us how we got it.
It's okay. It's probably going to take you guys longer to actually type this in for your answers than it is to actually do this problem. Do that problem, Alan.
Oh, wow.
Now, what am I asking for? Am I asking you to expand the whole thing like we did? Do I want all 11 terms? What do I only want?
The 7th.
Well, then I'm not going to build Pascal's triangle out to the 12th row.
Just go to the 7th.
I can't. I need the 7th term. You'd have to do all those rows to get there. But because we know that adaptation of the binomial theorem, I can find an individual term without doing a whole heck of a lot of work. If we had more time, I'd let you guys do it on your own, but I want you to have a little time to work on the group quiz together. So let's do this one together. That tells me I'd have 11 terms. I only care about the 7th. So I'm going to do this as placeholders. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What do I know each one of these is going to have? A 3x and a negative y. You do have to include the negative sign on any of your symbols, right? Your terms, which is why I was going to do another one here, but for time's sake, I'm going to kind of do this one instead. Same purpose. Then what do we say we could do? What could we find next?
Powers.
Good. How?
The sum. So they need to be the sum of 10, and it's 7th. So it would be the 10 minus 7. So 3 and then 7.
Which one's 3? Which one's 7? And are you sure?
X is 3, Y is 7.
Good. So if you don't know how to do this, check it out. Let me count it down. This is why I drew these blanks for you, okay? You could go 10, 9, 8, 7, 6, 5. Oh, shoot.
Oh,
I think you're actually wrong, Dustin. And there is a
Oh,
reason why, and that's because of the 0.
Yeah.
Right? So am I closer? Here's my point. Am I closer to the left side or the right side's end? Definitely the right side. So I would start on the right and I would count it down because it's just safer this way. 10, 9, 8, 7. This would have to be a 6. And once I know that that is a 6, then to his point earlier, he knows the sum is, for my exponents, the same as my original exponent. So we know the other one is actually a 4. And once we know those two things, how do we use the binomial theorem to come up with the coefficient? You guys remember?
And factorial.
over the 4 and the 6 factorial.
Very good. It's that easy. That's my adaptation of the binomial theorem because the binomial theorem as a whole is very messy. Right? There's a lot going on in different parts. Do you guys recognize this? This is actually the combination that I mentioned to you guys last week, the NCR, where it's n factorial over n minus r factorial times r factorial. So the way that they explain it a lot of times in a lot of books is they use this, which is also written like this. Ugh. It's too much. Take the original, divide it by the lesser powers of your term, factorial, and you're done. All we got to do is clean this up. Just be careful. Get this, do these, multiply them together. Let's make sure that we can finish. What would I cancel first?
The 6 factorial.
6, 5, 4, 3, 2, 1 with the 6, 5, 4, 3, 2, 1, which means I'd still have 10, 9, 8, and 7 over
4, 3, 2.
I don't even write the 1 either, Alan. Very good, because multiplying by 1 does nothing. We've done it a lot. Now I also know that I can cancel some stuff.
4 times 2. 8.
Good. 4 times 2 is 8. Excellent. What else?
The 9 and the 3, you can make that just 3 on top.
And what is 3 times 7?
21.
Times 10.
210.
Then I get 210 as my coefficient. And look how much I did. Blah. Alan, you can still do it. Because in reality, do you have to rebuild this every time? Or could you have started here and gotten all the way on down till you got the 10 there? Yeah, you could have.
Probably make a mistake.
Could have, I hope not. But yes, there's more chance to make a mistake. And this was pretty darn easy, wasn't it? But don't forget, you're not done. You still have to do 3x to the 4th, which means you got to do both of those things to the 4th because they're both in that set of parentheses. And do you know what 3 to the 4th is? Probably not, but do you have fingers? Yes. What's 3 times 3?
9.
What's 3 times 3?
9.
Well, there's my 4 3s. And what's 9 times 9?
81.
Yeah, it's not that hard, guys. So that is an 81. And x to the 4th would be x to the 4th. And then careful with the negative. when a negative is raised to an even power, we know that two negatives, we can make a positive. If there's an odd number, stays odd, stays negative. If there's an even amount, then we can take those two negatives and make a positive. Okay, so that means because this negative is raised to an even, it will just be y to the 6. So at this point, that's when you whip out the calculator and do 81 times 210 times x to the 4th times y to the 6th. And 81 times 210, you can see 17,010.
Oh, we have to, okay.
That, my friends, is what the 7th term is. And if you can fathom what we just did, it's, again, pretty mind-blowing. We took 3x minus y times itself 10 times, and we found the 7th term of that without foiling, distributing all of that mess, and then finding the 7th term. Look at all the work I did. That's it. Pretty cool. All right. That's all I got for you for this session. I hope that made sense. Good luck doing it on your own. Make sure that you follow all the rules and things that we talked about. Pay attention to the directions that they're giving you, and then make sure that you're using the correct formulas and paying attention to all the little details. All right.